Hello guys, once again welcome back to my channel Energy Zone. I'm Faye. Today I'm with a new video, and today's video is also based on chemistry, chapter 12, aldehydes, ketones and carboxylic acids, and this is part 2. So this is unit 12, aldehydes, ketones and carboxylic acids. The objectives are, after studying this unit, you will be able to write the common and IUPAC names of aldehydes, ketones, and carboxylic acids. Write the structure of the compounds containing functional groups, namely carbonyl and carboxyl group. Describe the important methods of preparation and reactions of these classes of compounds. Correlate physical properties and chemical reactions of aldehydes, ketones, and carboxylic acids with their structure. Explain the mechanism of a few selected reactions of aldehydes and ketones. Understand various factors affecting the acidity of carboxylic acids and their reaction. Describe the uses of aldehydes, ketones, and carboxylic acids. And as I have already mentioned before, this is part 2. If you haven't watched part 1, please do watch it. So we are going to start from the topic 12.3, physical properties. The physical properties of aldehydes and ketones are described as follows. Methanol is a gas at room temperature. Ethanol is a volatile liquid. Other aldehydes and ketones are liquid or solid at room temperature. The boiling points of aldehydes and ketones are higher than hydrocarbons and ethers of comparable molecular masses. It is due to weak molecular association in aldehydes and ketones arising out of the dipole-dipole interactions. Also, their boiling points are lower than those of alcohols of similar molecular masses due to absence of intermolecular hydrogen bonding. The following compounds of molecular masses 58 and 60 are ranked in order of increasing boiling points. So there is a table given. The B point B, that is boiling point, and molecular masses of the given aldehydes or ketones are given there. So first one, N-butane 273 Kelvin 58, methoxyethane 281 60, propanol 322 58, acetone 329 58, propan 1-ol 370 60. The lower members of aldehydes and ketones, such as methanol, ethanol, and propanol, are miscible with water in all proportions because they form hydrogen bond with water. Molecular structure when ketone is bonded with H2O. So let's move on to the next para. However, the solubility of aldehydes and ketones decreases rapidly on increasing the length of alkyl chain. All aldehydes and ketones are fairly soluble in organic solvents like benzene, ether, methanol, chloroform, etc. The lower aldehydes have sharp, pungent odors. As the size of molecules increases, the odor becomes less pungent and more fragrant. In fact, many naturally occurring aldehydes and ketones are used in the blending of perfumes and flavoring agents. It's an in textbook question, example 12.2. Arrange the following compounds in the increasing order of their boiling points, and the compounds are CH3, CH2, CH2, CHO. Second one, CH3, CH2, CH2, CH2OH. Next one, H5C2O, C2H5. Next one, CH3, CH2, CH2, CH3. Solution is, the molecular masses of these compounds are in the range of 72 to 74. Since only butane 1-ol molecules are associated due to extensive intermolecular hydrogen bonding, therefore the boiling point of butane 1-ol would be the highest. Butanol is more polar than ethoxyethane. Therefore, the intermolecular dipole attraction is stronger in the former. N-pentane molecules have only weak van der Waals forces. Hence, increasing order of boiling point of the given compound is as follows. First one would be CH3 CH2 CH2 CH3 less than H5C2 single bond or single bond to C2 H5 less than CH3 C2 CH2 CH2 CHO less than CH3 CH2 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 OH. 12.4 Chemical reactions. Since aldehydes and ketones both possess the carbonyl functional group, they undergo similar chemical reactions. First one, nucleophilic addition reaction. Contrary to electrophilic addition reaction observed in alkenes, please refer Unit 13, Class 11. The aldehydes and ketones undergo nucleophilic addition reaction. First one is mechanisms of nucleophilic addition reactions. A nucleophile attacks the electrophile carbon atoms of polar carbonyl group from a direction approximately perpendicular to the plane of sp2 hybridized orbitals of carbonyl carbon. Figure 12.2. The hybridization of carbon changes from sp2 to sp3 in this process, and a tetrahedral alkoxide intermediate is produced. This intermediate captures a proton from the reaction medium to give the electrically neutral product. The net result is addition of Nu- and H plus across the carbon-oxygen double bond as shown in figure 12.2. So this is the figure given here is the nucleophilic addition reaction. Second one, reactivity. Aldehydes are generally more reactive than ketones in nucleophilic addition reactions due to steric and electronic reasons. Sterically, the presence of two relatively large substituents in ketones hinders the approach of nucleophile to carbonyl carbon than in aldehydes having only one such substituent. Electronically, aldehydes are more reactive than ketones because two alkyl groups reduce the electrophilicity of the carbonyl carbon more effectively than in form. Now, next in-text question, example 12.3. Would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reaction than propanol? Explain your answer. The solution. The carbon atom of carbonyl group of benzaldehyde is less electrophilic than carbon atom of carbonyl group present in propanol. The polarity of carbonyl group is reduced in benzaldehyde due to resonance as shown below, and hence it is less reactive than propanol. Third one, some important examples of nucleophilic addition and nucleophilic addition elimination reactions. First one, addition of hydrogen cyanide, HCN. Aldehydes and ketones react with hydrogen cyanide, HCN, to yield cyanohydrins. This reaction occurs very slowly with pure HCN. Therefore, it is catalyzed by a base and the generated cyanide ion Cn minus being a stronger nucleophile readily adds to carbonyl compounds to yield corresponding cyanohydrin. Cyanohydrins are useful synthetic intermediates. The second one is addition of sodium hydrogen sulfide. Sodium hydrogen sulfide adds to aldehydes and ketones to form the addition product. The position of equilibrium lies largely to the right-hand side for most aldehydes and to the left for most ketones due to steric reasons. The hydrogen sulfide addition compound is water soluble and can be converted back to the original carbonyl compound by treating it with dilute mineral acid or alkali. Therefore, These are useful for separation and purification of aldehydes. This is the reaction between sodium hydrogen sulfide and a ketone, which is a reversible reaction. So the third one is addition of Grignard reagents. Please refer Unit 11 of Class 12. Next one is the fourth one, that is addition of alcohols. Aldehydes react with one equivalent of monohydric alcohol in the presence of dry hydrogen chloride to yield alkoxy alcohol intermediate known as hemiacetals, which further reacts with one more molecule of alcohol to give a gem dialkoxy compound known as acetal as shown in the reaction. Ketones react with ethylene glycol under similar conditions to form cyclic products known as ethylene glycoketones. So this is the first mention. The reaction that is mentioned over here, and this is the reaction that is mentioned over here. Dry hydrogen chloride protonates the oxygen of carbonyl compounds and therefore increases the electrophilicity of the carbonyl carbon, facilitating the nucleophilic attack of ethylene glycol. Acetals and ketides are hybridized with aqueous mineral acids to yield corresponding aldehydes and ketones respectively. Fifth one, addition of ammonia and its derivatives. Nucleophiles such as ammonia and its derivatives H2N single bond Z add to the carbonyl group of aldehydes and ketones. The reaction is reversible and catalyzed by acid. The equilibrium favors the product formation due to rapid dehydration of the intermediate to form C double bond N single bond Z. It can be alkyl, allyl, OH, NH2, C6H5NH, HCONH2, etc. Second one, reduction. First part, reduction of alcohols. Aldehydes and ketones are reduced to primary and secondary alcohols respectively by sodium borohydride NaBH4 or lithium aluminium hydride LiAlH4 as well as by catalytic hydrogenation. Catalytic hydrogenation. Refer Unit 11, Class 12. Second one, reduction to hydrocarbons. The carbonyl group of aldehydes and ketones is reduced to CH2 group on treatment with zinc, amalgam, and concentrated hydrochloric acid. Clemmensen reduction, or with hydrazine followed by heating with sodium or potassium hydroxide in high boiling solvents such as ethylene glycol. Wolff-Kishner reduction. So this is the Clemmensen reduction, and this would be Wolff-Kishner's reduction. Third one, oxidation. Aldehydes differ from ketones in their oxidation reactions. Aldehydes are easily oxidized to carboxylic acids on treatment with common oxidizing agents like nitric acid, potassium permanganate, potassium dichromate, etc. Even mild oxidizing agents, mainly Tollens reagent and Fellings reagent, also oxidize aldehydes. So this is the aldehyde, and when oxidized with a particular oxidizing agent, it will convert to carboxylic acid. So the reaction is really small. Ketones are generally oxidized under vigorous conditions, that is strong oxidizing agent, and at elevated temperatures. Their oxidation involves carbon-carbon bond cleavage to afford a mixture of carboxylic acids having lesser number of carbon atoms than the parent ketone. So this is the ketone. When it is oxidized, there will be a number of smaller carboxylic acid. First one would be due to the cleavage of C1 C2 bond, and second one by cleavage of C2 C3 bond. The mild oxidizing agent given below are used to distinguish aldehydes from ketones. First one, Tollens test. On warming an aldehyde with freshly prepared ammonical silver nitrate solution, which is Tollens reagent, a bright silver mirror is produced due to the formation of silver metal. The aldehydes are oxidized to corresponding carboxylate anion. The reaction occurs in alkaline medium. So RCHO, which is the alkali, react with 2AgNH3 twice plus 3OH minus gives RCOO minus plus 2Ag plus 2H2O plus 4NH3. Second one, Felling's test. Felling's reagent comprises of two solutions, Felling's solution A and Felling's solution B. Felling's solution A is aqueous copper sulfate and Felling's solution B is alkaline sodium potassium tartarate, which is Rochel's salt. I think that's how it is pronounced. These two solutions are mixed in equal amounts before test. On heating an aldehyde with Felling's reagent, a reddish-brown precipitate is obtained. Aldehydes are oxidized to corresponding carboxylate anion. Aromatic aldehydes do not respond to this test. So RCHO, which is an aldehyde, reacts with 2Cu2 plus 5OH minus gives RCOO minus plus Cu2O plus 3H2O. Cu2O is a reddish brown precipitate. So the third one, oxidation of methyl ketones by haloform reaction. Aldehydes and ketones having at least one methyl group linked to the carbon atom, methyl ketones, are oxidized by sodium hypohalide to sodium salts of corresponding carboxylic acid having one carbon atom less than that of carbonyl compound. The methyl group is converted to haloform. This oxidation does not affect a carbon-carbon double bond if present in the molecule. Iodoform reaction with sodium hypoiodide is also used for detection of CH3CO compound or CH3CHOH group, which produces CH3CO group on oxidation. So this is the reaction which is given over here. Okay guys, we have finished today's video. This third part of the video will be coming soon. I hope you guys like this video. If you guys like this video, you guys know what to do. Please like, share, comment, and if you haven't subscribed yet, please do subscribe and ring the notification icon so you can get the notification when I update another video. So that's all. Take care. Bye. Thank you.